now begin the contributor talks. I would request the session chair to kindly proceed.
Hello, welcome back to this last session of the second day of ASCAT. So, in this session, first talk is on search of three-state cell automata for clustering, authored by Sukanya Mukherjee and Arka Acharya, and it will be presented by Sukanya. Yes, Sukanya, start.
Thank you, sir. Today my topic of discussion is on search of three-state cellular automata for clustering, and another author with me is Prabha Acharya. He is a third year BTech CSC student of Institute of Engineering and Management, and this is also an outcome of our summer school 20 cellular automata 2024. The cyclic space of finite cellular automata are mainly attracted by the researchers not only for its theoretical aspects but also in the role of technological.
Just 1 minute because it is not being shared.
Full, yeah.
Yes, please continue.
Yeah. The cyclic spaces are mainly attracted by the researchers not only for the theoretical interest but also in the field of technological advancements. And one of the key point is here machine learning, where the single lens cycle attractors are mainly useful for pattern classification, and clustering also be handled by the multi-lens cycles CAs. That means the CS which are producing cycle length more than one. The key point of the clustering is that mainly two. One is the optimal number of clusters, and within a cluster, all the objects should maintain minimum distance with respect to the feature space. Now, till now we mainly targeted to use reversible cellular automata in the domain of for the domain of clustering. The reason for finding this cellular automata is that is a property of reachability, where every configuration in a cycle is reachable from all the configurations within that cycle. And specifically, we targeted to use previously the large length multi-length cycle CAs, and we can get it in reversible CA. And moreover, we are mainly focusing on the number of self-replicating RMTs also. If it is more, that means almost all, then definitely it's not suitable for clustering problem. So now we want to step out from this reversibility. We want to use only the multi-lens cycle, and that we can do in irreversible also. So in this work, we mainly focusing on multi-lens cycle. That means all the CA always generate the multi-lens cycle, and we call it as strictly multi-lens cycle. That means whatever be the CSIs, we figure out the rule which will capable of generating multi-lens cycles only. And this actually strikes in our mind, can we just extend the neighborhood? Can we extend the states? So here we started with the extension of state. We are just increasing the state count to 3, and mainly we will be focusing on uniform CA. Here we characterizes strictly multi-length cycle CA for null and periodic, but finally we will be using the null boundary, three-state strictly multi-length cycle CA for classification problem. To do that, we identify one major point. What is the proportion of non-self-replicating RMT and what should be the distribution? Only the proportion? No, the distribution is also important. I will be showing you. Now, there are few findings. The simplest way is that we make all the RMTs non-self-replicating, but it's not good for clustering problem because it will form small number of cycles, which is not good for clustering. If we just want add one impurity, just make one of the RMT say 000 as self-replicating, no guarantee of getting strictly multi-length cycle because always one single length cycle will be produced, which is 0 to the power n, where n is the number of cells in the CA. Next example, even if we give 52% non-self-replicating RMT, no guarantee of generating single length cycle, whereas 41% of non-self-replicating RMT makes strictly multi-length cycle. So the question is how we can figure out of this search space, huge number of search space, because when we are considering three-state tree neighborhood, that is 3 to the power 27 rules, how we can figure it out. So before going to that, I want to say what is the contribution of this work. Here we are actually representing the minimal sets of non-self-replicating RMTs for generating strictly multi-length cycles. Second is which are the useful CA rules for clustering. And third one, even if when we consider non-strictly multi-length cycle, what is the minimum set for non-self-replicating RMT. So these are the terminologies useful for my work. Here we are using an array of cells because we are using one-dimensional CA as three states. So the possibilities are of the states are 0, 1, 2. We use finite CA. So obviously we have to use boundary condition. Here we are using null and periodic both. And next is we are using three neighborhood architecture. So definitely as we are using three-state tree neighborhoods, so the possibility of RMTs are 27. And just the representation of one rule I have taken here. This is the way actually how we move from one configuration to another configuration by the help of RMTs, and we call it as sequence of RMTs. Next is these two are useful for our work, that is called as equivalent RMTs and sibling RMTs, where if you look at just arbitrary any row of equivalent RMTs, the leftmost value is different and all other remain same. And in case of sibling, just the rightmost values are different and all are same. Next, here you have huge space of rules. So we have to select the rules from 3 to the power 27 space. Now, the question is that two things are important. One is the self-replicating as well as non-self-replicating. So what is self-replicating? Self-replicating means if you just represent the combination of the leftmost, the current and the rightmost neighbors, just take arbitrarily 0, 1, 2. And if the middle bit is not there, so in case of 0, 1, 2, middle bit is 1. So other than 1, if you get 0 or 2, then it's non-self-replicating. When you are getting 1, it's self-replicating. Now, this is the sequence of RMTs. One interesting point is that if in a RMT, all the in a RMT sequence, if all the RMTs are self-replicating, then we may not get, we should not get anyway strictly multi-length cycles here. So we have to keep this thing in our mind and we have to design the rule accordingly. This is the cyclic space. Here you can see this is the representation of irreversible strictly multi-length cycle, and we are finding actually 3 cycles over here. Previously, think according to our concept, previously we are looking only on the cycles for the clustering. So if we go in this way, we miss some of the configurations, yes or no? Because yeah, some of the configurations can be mapped to the real world data. So what we are doing actually, we are considering the entire graph for the clusters. So very simple way is what actually the lemma shows that in every RMT sequence, we should not get any RMT sequence where actually all the RMTs are self-replicating. Now, how we can do this? First, we make all 27 as non-self-replicating. We can get some space, though it's not useful. then we are reducing that number. So we are just increasing the number of self-replicating. It can be 26, 25, but how can we manage? And even if I am showing you one example, just by making this 8 9 the RMT is non-self-replicating, we can get strictly multi-lane cycles here. But is it useful? How can we proceed? It's a huge search space. So we move for that to de Bruygerian graph. So by the help of de Bruygerian graph, we try to solve the problem. In case of de Bruygerian graph for three-state tree neighborhood, we have 9 nodes, and from every actually node, we are getting three incoming edges. There are three incoming edges for every node, and three outgoing edges also. So what we are planning to do here in this graph for periodic boundary CA, we will be specifically finding the elementary cycle, because any RMT sequence is actually formed by the elementary cycle. So in every elementary cycle, if we make at least one of the RMT non-self-replicating, I think we will be successful to get the strictly multi-lane cycle. We do the same thing for null boundary also, but in case of null boundary, there is some specification actually. The starting node can be either 00 or 01 or 02, and the ending vertices will be 00, 10, and 20. So when we start from 00 and when we are coming back to 00, definitely we are considering the elementary cycle. But other cases, we are considering the elementary path. And again, the RMT sequences can be generated by the combination of elementary cycle and elementary paths, or only the elementary cycle. So our objective is to make what? Any one of the RMT. Here RMT means what? Every edge is actually representing RMT. So if any one of this, if we make non-self-replicating, so the corresponding RMT sequence will not be making any single lane cycle. So in this way, actually, we identified by the help of de Bruygerian graph 148 elementary cycles in periodic boundary and 407 elementary cycle and paths in null boundary C. And this is the result. Actually, this number of 1 RMT means actually we are getting 3 elementary cycles where the number of RMT is 1, 3 elementary cycle number of RMTs are 2. In this way, we make it. Next is what? Valid set. Valid set means what? In the initial phase of my talk, I told you only the count is important, or the proportion or the distribution. Which RMTs needs to be non-self-replicating. So from there, what is the idea? Try to understand when we have 148, just for periodic boundary, I'm saying 148 number of elementary cycles. I should design that 148 cycles in such a manner from every set there should be at least one non-self-replicating RMT. Okay, so for that actually we figured out in case of periodic boundary 11 RMTs needs to be non-self-replicating, and for this should be null boundary. The null boundary, it should be 7. And here we mentioned about the distribution. Next, from this we can identify at least how many strictly multi-lane cycles we can get for null boundary and periodic boundary both, and we can say that if the number of RMTs less than 7 in null boundary, we don't have to check the corresponding rule. We can say it's never applicable for our purpose, clustering purpose, because it will not generate strictly multi-lane cycles. So this is the example I have taken. Just think for pattern classification, clustering problem. Just see if 101, 111 and 102 are taken. Are they in same cluster? The answer is yes. Why? Because now we are looking reachability in different fashion. We are seeing whether a particular object or configuration attracted by some cycle or not. If we look at the graph, 101 is will be actually reaching to the cycle of length 4. 102 also will be reaching to the cycle's length 4, and 111 is the part of the cycle. So this is the key idea of our clustering in this work. So for clustering, what is the requirement? Cycle reachable from large number of configurations and moderate number of self-replicating RMTs. So this table shows actually when we are considering 7 non-self-replicating RMTs, what are the possibilities of RMTs? So in this way, we have got 16 possible valid sets. I am showing it for the null boundary condition. And how we are making the arrangement? Yeah, here again the concept of information propagation comes in the picture. And definitely if we make the arrangement like this, all the sibling RMTs or the equivalent, and as well as all the equivalent RMTs have the different values, so we expect large length cycle. But there is some restriction. What is the restriction? As we are actually mainly targeting for strictly multi-length cycle, it is not suitable. The reason is why sorry. Yeah, the reason is why here, if we just look at here, suppose we are making 12, 21, say non-self-replicating, and if we consider the sibling or just here 6, 7, 8, these are the non-self-replicating. So when we are considering 6, 7, 8, so when non-self-replicating, 3 of them having uh, 2 different values, 3 of them don't have the 3 different values. Okay, so that's why actually we have to make some uh, uh, alternate option. That means initially our target, we want to make all the sibling and equivalent RMTs are different. Now we are just moving that restriction, and we are making like this. In this case, what we are doing actually, we are finding say 178 rules, 1728 rules, and we are selecting the, or just generating, selecting the rules in such a manner where RA equals to RB but not equals to RC. So in this way we are getting a pool of rules, and finally out of this we checked each of the rules and we identify 5504 are the useful rules for clustering. But the question is that out of 554 which are effective, we actually have done the experimentation using these rules on these data sets, iris, body move, and user knowledge. And we identified few of the rules, 3-state 3 neighborhood rules, which are effective depending on the CLO test score and down index. And finally we compare. When we do the comparison, yeah, here we are getting exactly same, better. Better means 0.63 and 0.68. But if we look at here, this is the best result is 0.35, but we are not just closing to the best, we are closing to the other results. Here also you are finding the same thing. The point I want to mention here, previously all the times when we did the clustering in our previous work, we always actually perform the merging. Here we are not performing the merging, only the direct CA we are using. Next, we are targeting to use if the length of, if the number of non-self-replicating RMTs are less than 7. So what is the thing? Do we get only single length or single plus multi? The answer is yes, we can get always strictly single length cycle if there is no, definitely no non-self-replicating RMT. If one self-replicating RMT, then also we will get always strictly single length cycle. And if we get two non-self-replicating RMT, then if this property is satisfied, then we can get, I have taken one example, if this property is satisfied, we can get single length cycle of length 2. So I have taken this example. One of the example is this. So if we just make the 9, 12 as non-self-replicating, or 9, 15 or 12, 15, so we will get the non-self-replicating RMT. So we can claim that if the CA is if the CA is non-strictly multi-length cycle, then also we can get multi-length cycle, and the minimum count of the non-self-replicating RMT is 2. Thank you.
Thank you, Sukanya. Time for question. Anyone?
For iris dataset, how do the encoding?
Encoding was the same approach, generally what we do in the frequency encoding, but here I want to tell you, first we make the bin, 3 bins we are making. The first one is mapped to 0, second one is mapped to 1, third one is mapped to 2. There is no concept of having distance.
Okay, so only four cell length CA used for
Yes, I
iris.
am using 4 cells. And
Okay.
every time here we are just, yeah, I should mention it. Here I am moving out from the Hamming distance concept also, because yeah, you can change it also. First one will be mapped to 0, second one you can map with 2, and third one also you can map to 1.
Okay.
Different CA will be selected, but you can get the same kind of
So,
performance.
total number of configuration 3 to the power 4 will be there.
Initially 3 to the power 4. So I should say the first level encoding is encoding when we are doing the encoding. Yes, yes.
My question is, in iris dataset only 150 data points are there. So this much huge configuration, everything you are storing, or only this 150 points you are
No,
storing?
after encode, first we encode the data. On that we are doing the clustering. Then again we are just mapping the encoded to the real data, and then we perform the Silhouette score or done index, whatever.
Okay. Okay. So this 150 points.
First converted to CA configuration, just we do previously also. Here 3 state, 3 neighborhood, that means the representation will be in 3 different digits, 0, 1, 2,
Okay.
and this will be converted into 4-bit. Yes,
Okay.
because 4 features are
So
there.
here only this 150 configuration is using, or all the
No,
configuration?
no. 150 will be converted here. Then no, what are you asking?
My
Yeah,
question is,
yeah. Hmm. Yes. See, yeah, I'm just, yeah, that we cannot avoid. We are starting from one configuration and we are moving to next, and finally, we need not to store the entire cycle. You can store just one member from the cycle.
but here this
Yes,
is
and
not reversible completely.
no, not reversible. See, it can be reversible, it can be irreversible also. Okay. If worst case, I'm considering if worst case maximum it is large length cycle, then you are exploring all the configurations. Otherwise, otherwise it is strictly multi-length cycle, and you are understanding from yeah, you are understanding from here also the rule is balanced or not. If the rule is not balanced, then initially this is not the part of reversible. You try to think whatever the way we have designed, if it is not balanced, first of all, then there is even, yeah, if not balanced, if the cycle length is large, then yeah, that we cannot avoid, we have to explore.
Okay, so you can discuss it, continue the discussion. Yeah. Yes.
Would be very silly because uh, reversibility is not the issue, right? It is not a
No.
necessity. It is
No,
not
sir,
the
I'm just,
necessity.
yeah, stepping out from reversibility. I'm just looking only for the cycle. It can be reversible, irreversible, anything. Cycle in
But
the
how do you ensure that the cycles of your choice are arriving?
So that's why actually we are concentrating on the strictly multi-length cycle. So there should not be any single length cycle. Okay, all the cycles will be multi-length. One of them can be, yeah, one of them can be reversible. When
Now,
we
how do you ensure that? One has to be reversible. One of them is reversible means what?
No, sir, I'm saying I'm not actually focusing on reversibility. I'm focusing on only on the single multi-length cycles.
Now,
It may be reversible.
now you said that you are that is not the necessity. Reversibility is not the
Not
necessity.
necessity.
So pushing aside,
Hmm.
then how do you ensure that your desired cycles will be coming?
Desired number of cycles.
Desired cycles. What is your expectation?
Yeah.
Those things should come. You should ensure that without reversibility, they should come.
First of all, the design is like in this way, always we get a multi-length cycle. Yeah.
Maybe the result is
Suppose the desired number of clusters is suppose 4. Okay. So there may be some rules out of all these rules who will give you 4 cycles. So then the purpose will be fulfilled. Yeah, then the time complexity may increase.
Yes, actually here the objective is that we want to judge the quality of CA without any margin. It's a just first level phase. I want to see the behavior of CA or the significance of the rules which can do the clustering without any help of margin. Generally in any trend in machine learning also, what we do, we have the scattered all possible objects. Then we march, and that marching level by level we are marching. But here just only the scattered objects, just by the say in one level we want to see how the clustering is going on. That's the fact.
so okay.
Beginning of work, yes.
Yeah, yes. What she has done based on the experiment and some theories that will be
Yes.
okay. Once again, thank you, Sukarna. Thanks, Sukarna. So we have to move forward. So our next exploring opinion dynamics through social influence, online communication, and leadership, a fuzzy approach. It will be presented by Aradhya Chakrabarti, and co-authors of the paper is Niharika Rana, Sanchit Baweja, and Rinkaj Goyal. Height first.
Hello. So good afternoon, everyone. On behalf of all my co-authors, I'll be presenting our study titled Exploring Opinion Dynamics Through Social Influence, Online Communication and Leadership, a Fuzzy Cellular Automaton Approach. So this is a simulation study, first and foremost, in which we prepare an opinion dynamics model which in itself is kind of a non-deterministic field of study. And we extend a model of opinion dynamics called Hexelman-Krauss model using something called normative social influence and online communications. I'll talk about all of them in detail. So we try to describe them through somewhat of a structured approach. And in doing so, we use cellular automaton states, which are fuzzified to model uncertainty and opinions. So let me talk about the motivation behind a study. So nowadays, through the growing global scale of communications, there is an unprecedented increase in shaping of beliefs from interactions with people who are at very large distances away from us. So in doing so, we cannot just consider local interactions to be the only factor that is affecting opinion formation. So and why we need to study opinion dynamics? It is in order to study how the study the different behaviors of different kinds of population configurations. So, oh wow, sorry about that. So before moving forward, let us consider some previous models of opinion dynamics, not necessarily related to cellular automaton, that were proposed. Most of those were proposed before the internet age. So particularly the bounded confidence model, which was proposed by Defuant et al., and the snatched model, these consider only a few aspects of opinion dynamics, but they do it perfectly. However, we as a group, we wanted to take a more ensemble approach, and along with opinions, we also wanted to extend. We used the Hexelman-Krauss model, and we extend it with normative social influence and online communication, which I'll discuss now. So what is the Hexelman-Krauss model? So in this model, we consider an agent in a population to have a confidence threshold. Any other agent, this is a stochastic model, in any other agent in the population whose difference in opinion from that agent, which lies below that confidence threshold, will be in the confidence set or interacting neighborhood of that agent. So when the evolution occurs in the next time step, the current agent will take that average opinion of all the interacting neighbors. So if you take a look at this diagram, this is a 2D grid which considers an initial random assignment of opinions. This is, instead of stochastic model, we just consider local interactions for the SK model. This is a basic starting step for our whole simulation study. So you can see that most of them converge towards 0.5, which is the opinion that we consider to be neutral between 0 and 1. So now moving on to normative social influence that I've talked about. Normative social influence, we consider from Ash's conformity experiment, if some of you might have heard about it, from 1950, which says that when put in a group where a person sees that a majority of the other people are believing in something, whether it be right or wrong objectively, the person also tries to fit in with that, even if they privately hold different beliefs. So we consider a mathematical model of conformity that was previously defined by Epstein and Smaldino. And in that, they consider this something called ideal opinion. And in that, they define this distinctiveness factor, which is just how farther from the mean opinion can a person go. So we, by ourselves, define NSI, which is a theoretical aspect as such. We define it mathematically to a force that updates this distinctiveness factor. Okay, so next is our version of distant neighbors, which we have defined. It is just the first theta. Theta is accessibility, or the number of agents a particular individual can access at radius r. So if the radius is 3 or 4, it will access a few of the agents at that radius in a 2D grid. Now, when we are modeling a population, we need to consider all the constituents of that population first. So how do we model it? First, we'll have to consider the observable region or the community or the population. We consider that to be a 2D grid. Next, we have the agents, which are the main individuals in that population. They are considered as the cells in the grid. And the basic state of the cell will be opinions. Other than that, since we are considering an ensemble approach, we also add attributes to those agents, and these attributes can be dynamic or static, and they describe the external influences on that agent. Next, we'll have the transition model, which we'll talk about through the local rule and the fuzzy rules of interaction, which we have defined further. So our version of the CA, the 4 ingredients of our CA are described here. I won't go much into detail about it, but we use the Moore neighborhood. We have 5 fuzzy states. I'll come on to that because we define fuzzification later on. We also define that periodic boundary conditions are followed. And since we are modeling a very non-deterministic thing, opinion dynamics, that is why we consider fully asynchronous updation. Because in synchronous, it does not really make sense. Everyone is not interacting at every point of time. So now coming on to the parameters, which is one of the main things in our study. So there are various kinds of parameters that we have defined. In the next slide, I'll come on to that. But just glazing over them, I'll talk about some important parameters. The first one is whether an agent can get negatively influenced and retain that negative influence over its neighbors. That is dissenter. It is a Boolean parameter. We also have the accessibility, which I have also defined here, the initialization of accessibility. I won't go into the details as much, but there are a lot of parameters that we have defined. Now, and all of these parameters lead to the changes in the population over time. So these are all of the parameters that we have defined. However, the main thing is some of these parameters can dynamically change along with opinion. In a CA, generally only the state changes, but since we're considering also the parameters, that is why some of them, which are the main parameters, they also change over time. So we have defined these parameters based on their impacts, which we could actually utilize to define real world scenarios. So for example, the dissenters tend to retain their opinions. So they would, even the dissenters and the leaders have a larger influence area. So these kinds of agents, the density of these agents would dictate the final state of the configuration. So the local rule that we have defined. First, we define the local rule based on the crisp values. Crisp values is just the continuous values that we have considered that we define initially. Let's say for opinions, it's from 0 to 1. After that, they are fuzzified. So first, we consider the interacting neighbors to the confidence set according to the HK model. The distant neighbors are added. Then according to that, we calculate the average fuzzy opinion according to conformity, and then according to the HK model, we just assign that to the current agent. After that, the parameters come into play. Accordingly, they have a few different kinds of methods of updation that I have not defined here because for the sake of brevity, but there are a few ways which we utilize. So through this, we are going to find the fuzzy rules of interaction. Since we are defining since we're using fuzzification, we consider Gaussian fuzzification, where the mean value describes the actual value of the parameter, and the standard deviation shows the uncertainty in the value. And we also define for opinions and average opinions 5 fuzzy categories, for NSI coefficient 5 categories. So upon considering all of the possible combinations of all categories, we find that there are 2 basic rules of interaction. If an agent is a dissenter, it tends to retain its opinion. If an agent is not a dissenter and its parameter combinations lie in the following 16 categories, then we see that they all evolve to neutrality, which is interesting because neutrality is generally not even considered for most opinion dynamics models. That is why that is going to be one of our conclusions later on. So this is the general methodology of our simulation study, and we considered 3 different kinds of populations for our experimentation purposes, which I'll come to next. So the first population that we consider for experimentation is ideal population. We define an ideal population as a population with all agents who are non-dissenting, offline, and non-leader. So all of the parameters are not there, and everyone has the same opinion at the beginning, not neutral. And we see that all of them converge to complete neutrality or complete consensus, a complete steady state. And this rate of convergence shows a polynomial rate of growth, which we can see here. And this is dictated by the diplomacy is dictated by the number of dissenters or the inflexible non-conformists that I've defined here. Next, we consider mixed populations, which is just a variation of ideal populations, but with varying kinds of opinions and parameters. And in this also, we see that the number of neutral opinion holders increases, although it will never actually completely reach neutrality. Now we use a statistical measure called the Herfindahl-Hirschman index, which is generally used for studying clustering among datasets, and we use it to identify cliques in our own model. So using this HHI, we can see that higher the dissenters, higher the extremity of the initial HHI, which validates our the previous conclusion that we got from the ideal population experimentation. That is, this diplomacy arises from inflexible non-conformists. So higher the number of dissenters, higher the HHI. So that means that there is a consensus. That is 1. So next, an interesting part of our experimentation is the clustered population. So we define clustered based on outliers. So we define outliers as agents who are leaders, dissent, and have an online presence. So when an outlier is placed in between a cluster, and we can have 2 kinds of clusters. If an outlier is at the center and they are surrounded by normal opinion holders who have the same opinion as the outlier. The second type of cluster would be everyone is an outlier, or at least more than the single central agent. In the first case, we see that the clusters dissolve over time. And we are only considering the dissolution of the clusters, not the formation. So we see that when a single powerful or person or an agent who shows a lot of I mean, effect on its followers, it dissolves over time if it does not have any other person who is willing to actually accept that and continue. However, when we see in this graph, especially when it's 3/4 of the population has this tendency to also get that extreme opinion, or also continue with that polarized opinion. This cluster that we see, a lot of nice patterns are also found, but I have not shown them here for brevity purposes. But this kind of cluster then carries forward throughout the population over and over, and it does not end. So this is the general experimentation that we have carried out. This is only a simulation study, and the first ideal population and mixed population results can be summarized here. But this especially validates a previous statement that was defined by another research paper, that full consensus is easy for competition of up to 3 opinions, that is 3 fuzzy categories, but difficult for 4 or more opinions, which we have seen and validated. Similarly, sorry. Next, we considered the results from the clustered populations, and we see that when there are more number of at least 75% number of outliers in the whole population, this polarized opinion is carried forward by propagation through an ever-growing network of these clusters. And future work might be hypothetically to use this to mitigate bias by actually finding the origin of the polarized opinions. Sorry. So, of course, this is only a simulation study. We have not validated this using any real-world data, but this is something that we intend to do in the future. And also, we are greatly simplifying the complex social structures that are more like complex networks. But we are happy with the kind of results that we have found. And obviously, empirical validation and extended modeling are required. So, this was conducted as part of the Indian Summer School on Cellular Automata 2024. Thank you.
Thank you, Aradhya. So the time for question. So question from audience. Yes.
I'm interested in that outlier model. How this you were saying that clusters are not dissolved. Is it growing?
Yeah, I should have put that in the pictures. But the thing is, these clusters are of the same size. But let's say the left 3, they can be of any size in the beginning, but the size remains same. The cluster just moves through the population over time.
Oh, it's not like its followers are increasing. It's
No,
not like
it depends. Sometimes it can, according to some circumstances or some parameter combinations. But generally, in almost every case, the whole cluster just moves throughout.
Okay, so and you are choosing only one leader.
Yeah.
Rest of the part are followers.
Yeah, this can be there can be multiple clusters in the population also, but we're here just to show
you have
for
tested with
demonstration.
only one.
We have tested with multiple only, but just for demonstration purposes, sorry, there is only one cluster in the
Okay,
picture.
no, I am interested to understand like how it is behaving.
Yeah, the clusters. I mean, the initial polarized opinion. If the first person that had that initial polarized opinion, if they overcome that opinion and move towards consensus, another person from the initial cluster will become the leader, and then over and over and over and over, this cluster will move forward.
Is kind of propagating the
It's kind of propagating. However, that is not that close to real life. It is generally when most of them are not leaders or willing to take that polarized opinion, where we see dissolution, which is seen in most friend groups, most groups who tend to go against the norm, or something like that.
Okay. Good work.
I have a small question with that slide. Which update you are using?
Fully asynchronous, only one.
So that is very important here, according to your question. Look, for the first picture, so they are actually remain concrete. They are not moving, because here you have selected 8 cells, and they all are neighbors of each and every one, and they are not updated together.
No.
Okay, maybe the reasons why the other pictures, there are the group with some distances with each other, like the topmost cell and the downmost cell, they are not neighbor. So they are updated, uh, not updated in the same time step. So therefore, the middle one actually taking the advantage to make them separate. So maybe with that model, if we change the updating scheme, that reflection will not be reflected.
Yeah.
And then all those theoretical claim you are claiming according to the population, that influence and all these things, that may be challenged
not hold
because
true.
of this is only the updating scheme actually playing the role to make this kind.
Absolutely. Through synchronous update, it all moves towards consensus very
Yeah.
fast, because everyone is having at least one neighbor which will have the neutral opinion. And through the HK model, we have already seen in the initial slides that they tend to move towards neutrality. We can't do anything about
But
that. So
the problem is that fully asynchronous update is not, it's obviously very important in terms of distributed system, if you consider the mutual exclusion problem and all these things. But in our society, sometimes the neighbors follow the same clock. That means they are not following the fully asynchronous update. Like our sleep cycles are somehow related with our family members and all these things. Similarly, our the way we adopt ideology is also somehow related with our friends. So we and everyone loves to live in our comfort zone. So if someone is with some extreme right ideology, they have friends only with right ideology. If someone is with left ideology, only with left ideology. So for that case, the fully asynchronous update will not work. If you change the update with some other alpha asynchronous and all these things, maybe you can able to validate the things more socially with that.
absolutely, we could work on that in the future.
Any more question? Acha, Aradhya, that 2 points,
Yes,
2
sir.
comments from my side. So your rule seems little bit complicated.
Okay.
Since you are using fuzzy CA, it it is becoming complicated. That I understand. But in future work, target should be to not to make it more complicated.
Okay.
Make it as simple as possible. Number one. Number two is your dimension is 2. What if it is you shift to 1 dimension or 3 dimension, etc.
Yeah, we have to
Yes,
work on that
that 2 point you may consider.
for sure.
Thank you, thank you, thank you,
Thank you, sir.
For the good presentation. So by these 2 talks, we have to conclude this session. Yeah. So thank you everybody. This is the last session. So okay, you please cut.
Thank you, sir. Now I would like to invite Shruti Garg ma'am to present a token of appreciation to our session chair.
Okay, so at the end of this session, I just would like to say that three of our participants will leave today or tomorrow morning. So we would like to distribute these 3 certificates today. And I request Shruti ma'am also to again distribute the certificates. First is for presenting the paper. I request Shobhik Roy to please come over here. His paper is First Experiments on Chaotic K Non-Uniform Cellular Automata. Next 2 certificates, one is for active participation of Jayanto Pal. I request him to please come over. Active participation for of Shutopa Chatterjee. One important announcement. Today we have banquet dinner at Kake Resort, and for that we will leave the campus at 6:30. At exactly 6:30 p.m., a bus will come at the R&D building here outside this building, and I request those who can come to R&D building at that time, they will be picked up by that bus. After that, the girls' hostel is near to the PMC Chowk bus stop. The bus will see Chowk.